Now this question, it is also MSQ and it's also very, very tricky. And if let me show you the answer for it is A and C. And many of you might have made mistake here. The reason is it can be answered using, I mean, you have to use multiple sources. First is that you have to know the modulus of the, to differentiate, you have to know modulus of the nylon fiber, ethylene, rubber, and styrene. Which one will have high modulus, which will have lower modulus. You should have a pretty good idea. Because see, the slope is changing everywhere. The slope of one is highest. Slope of stress resistance curve is modulus. Right? So it's your one is having highest slope, means it is having highest modulus. So definitely your fiber will have highest modulus. No doubt. And also they will show you very less plastic deformation or no plastic deformation. Like if you see the glass polymer, they are just like this. Carbon fiber, they are just like this. And in your polymer fibers, like glass nylon fibers, they can give you something like this. Okay. But definitely have a very high modulus. So that nylon fiber could be one. And also if polystyrene is very brittle, then also you can get this. So A and C could be answer if you check this. Now, if you go for A, now let's check for others. Does it fit with all the curve? So 2 is polyethylene. 2 is polyethylene, and that can be true. Okay. Now 3 is vulcanized rubber. That is also true. Vulcanized rubber will have relatively large elongation, and since it is vulcanized, so its modulus will be enhanced, because with increase in cross-linking density, your modulus increases, if you remember. So this 3 could be a vulcanized rubber. And now here is the trick that many of you will not consider A as answer. The reason is you will think like polystyrene is very brittle. How it could be such a long percentage elongation? But it is not telling that the grade is glass grade. It could be expanded polystyrene grade, expanded grade. So it's always glassy. Expanded polystyrene is one form of foam grade of polystyrene. It can show you very high elongation. The 4 is very much is the polystyrene. Which polystyrene? Expanded polystyrene. Now let's check for C. First is polystyrene. That means this polystyrene is not expanded polystyrene. This polystyrene is brittle polystyrene. See how they have mixed a lot of things, like types of polystyrene also. Okay, that's why it becomes multiple select. Otherwise, it's very difficult. Okay, polystyrenes can also be brittle, so one can be also answered. Second is nylon fiber. Now they're telling, see, this could be nylon, and this could also be nylon. That means they're telling nylon is not just a single nylon. There are many types of nylon. Nylon 6, nylon 6, nylon 610. So this could be my nylon. This is a different type of nylon. This could be different type of nylon. Can both be a nylon? Yes. This nylon is relatively higher modulus than this nylon. And of course, this nylon is not showing a lot of plastic deformation. See, it's a fiber. It's showing very less. Okay. Now, polyethylene is our third one. That is true. It could be polyethylene. It is showing relatively good good elongation. And of course, vulcanized rubber is this one. 4 could be vulcanized rubber. Okay, this could be a vulcanized with high elongation. Now, why B cannot be answered? So one cannot be polyethylene, because polyethylene is not a brittle at all. Got my point? It will show you some plastic deformation. So it could not be answered. So, and D, one is vulcanized rubber. That's not possible. Your vulcanized rubber it will always be very long. I mean, it will show you good elastic deformation. And also, it will not be brittle at all. Okay. So A and C is the answer. Now, to make it more, to state it more confidently, we can think for different modulus values. If I show you modulus value, so you see here, your nylon fiber has the 2 to 6 GPa, and glassy polystyrene is having 3.5 GPa. So nylon fiber is having higher modulus in one case, as compared to and in one grade polystyrene is having higher modulus and nylon is having lower. Nylon is having lower. And this is polystyrene. That is possible. See, polystyrene is 3.5 GPa. I'm talking about glassy, and nylon fiber is 2 to 6. So in one case, your nylon could have 6 GPa. There are many types of nylon. I will show you different nylon fiber and their 6 GPa. In 6 GPa case, nylon can be this one, which has higher slope, and 3.5 is lower. This could be polystyrene. Got my point? Or polystyrene could be, this could not be, but this could be a definitely polystyrene in one case, and this could be definitely nylon in another case. Got my point? Because some nylon has higher modulus than styrene, and some styrene has higher modulus than nylon. So they can be, this could be both. Okay. Now if you see your expanded polystyrene, such a low modulus, 50 to 250 MP. Low means this one, and will have very high elongation also. I will show you. So this could be a polystyrene but expanded grade. And you see here definitely. Here you see your, in one case your polyethylene having lower modulus than nylon fiber. That's true. Nylon fiber is in 2 to 6 and polyethylene is 0.1 to 1.5. Anyway, there is no competition. Okay. So from this all, now if you, I'll show you really realistic data from literature. So here are the typical expanded grade. See, such a high, very low modulus and such a high percentage elongation, right? As you can see here, this one, it can replicate this one. 4. Now, polystyrene could be this also, very high brittle, right? Very high modulus. As you can see, polystyrene has very high modulus, 3.5 GPa. Some nylon could be inferior with respect to polystyrene in terms of so as you can see here, your styrene is such a, this is real data, okay, brittle as compared to polyethylene. Okay. Now I was talking about nylon. Nylon is having range from 2 to 6 GPa. So as you can see this one is nylon 6 heat treated. Okay, as you can see here. And one, this is nylon 6, it is having lower, slightly lower. This is nylon 6 is stable form, which is very low. So it's coming from 2 to 6. That's good range. Okay. Bulk noise is going to be typically having this kind of. By combining all this together, you may arrive that there is a lot of concept involved here to come to the answer A and C. Now, question number 125 is also MSQ. Answer is very typical. I mean, you don't need to think about it. It is polystyrene. So styrene is something which will be polymerized by all of them. Anionic, cationic, free radical. Okay. So definitely you are going to use free radical and ion. Ring opening is not possible because there is no ring in styrene, and polyconcentration is not possible because there is no two functional groups. I mean functional group, not a double bond. Okay. And if you know free radical, it is MSQ, so you should definitely think of ionic. It is by name, it is MSQ. Actually, it is making very easy to find its techniques that is used. Okay. Now, A and D. This is very typical question. Here, actually, it should be mentioned like using what model you should estimate the compliance. Like you can use Voigt model, Voigt element. Definitely, you should not do Maxwell element for compliance or for creep experiment, because Maxwell element tells you like something like this. With the time, how strain is changing, something like this. That's very poor estimation. This is the instantaneous strain, and from this to this, this is exactly same as this, that is elastic deformation is recovered, and whatever you are getting here from here to here, this is coming from your retarded strain. It's very poor because the actual polymer will show you something like this. Something like this. You have an instantaneous elastic deformation. Then you have a e to the power minus t by tau, retarded with function of e to the minus t by tau, retarded strain because of viscous behavior of material, and then you have a recovery. Sorry, it should be, I should put you recovery element also, recovery, this one, and then you have elastic deformation recovery, and then you have recovery of viscous element, and something will be plastic. So to get this exactly, to get this, what you call it, I mean your Voigt element, Maxwell is very poor estimation of creep. Definitely we are not going to use Maxwell expression, that is a ln of t equals to sigma naught by E plus sigma naught by eta into t. Okay, where this term is telling you about sigma naught by eta into t. I mean, you can use here also the experiment expression for compliance. Epsilon of t equals to sigma naught 1 by E plus t by eta, and epsilon of t by sigma naught equals to 1 by E plus t by eta, and epsilon by t is equals to 1 by E of t equals to 1 by E plus t by eta, and 1 by E of t is compliance. So compliance is 1 by E plus t by eta. So using this Maxwell element also, you can arrive with the compliance expression. E is already given, and eta is already given, and tau is already given. I mean, time is already given. So you can estimate. If you estimate, your G of t will come around 3. But it's a very poor estimation. Actually, it should be mentioned in the question itself which model you should use to estimate compliance, or to follow the creep model, which model you want. But we'll use our Vivek to try to figure it out what is the best one. Now, if you, this is the actual polymer which has having viscous plus elastic behavior, actual creep behavior. The nearest one is Voigt, which tells you, see, I cannot tell you about the instantaneous deformation, but I can tell you about the retarded strain, and then the recovery. There is not this instantaneous recovery also. So it ignores the instantaneous elastic strain that is going to recover. It only considers viscous retarded strain as well as retarded recovery. For this slope, so this value is given by, I'm talking about Voigt element, sigma naught by E, and this is going to given by, sigma naught by E to the minus t by tau. So exponentially it's going to decay, and the slope is given by sigma naught by eta, initial slope. So what I think is you should use Voigt element for creep experiment. That is very much. For that you can reach to the compliance expression, that is J and minus t by tau, this, right, or 1 by E, 1 minus e to minus t by tau. Here you can put E value, t value, and tau you can calculate using tau you can eta by E. So you can put here what the compliance you will get is 1. Of course, you will get 1 GPa inverse, which is nothing but 1 into 10 power minus 9 meter square per meter. Newton per meter square is Pascal. Okay, so answer is here 1. Here you're getting 3. Okay, the best so according to me, the answer for this question should be 1. Okay, as simple as that. But the best model that will estimate the creep or compliance within certain time will be combination of both Voigt and Maxwell. We call it 4-parameter model. What do we call it? 4-parameter model. In 4-parameter model, so here what we have considered is one elastic component and one viscous component. That is my dashboard. It is attached in a series, and I have given constant load. So what is how strain is changing with time? Okay. Here in this case, I have assumed I have not taken a series. One elastic component I have and one viscous component I have, and both are attached with parallel. So our material, this is how the material is showing viscoelastic we have here. Okay, with the constant stress, how creep is changing with time. But actual, which is actually this one, because we need this instantaneous deformation in my creep. Right? If you remember the creep experiment, your graph will be something like this. This is the primary reason. This is the steady state secondary reason. I mean, somewhere up to this point. Okay, and then this is the rupture or tertiary reason. But you see, this is what we are getting. We are estimating this one, and here this is what is the retarded one. And this reason we don't get, because at constant load, okay, when we do creep experiment, we never get this rupture zone. Instead, we give this continuously constant secondary creep, secondary reason. It will take years to reach to the tertiary or rupture state if your load is constant at room temperature. At high temperature, your creep time will be reduced. That is how the time and temperature superposition principle has come. Okay. Anyway, so that is what we want to estimate. So what is lacking here in Voigt model? What is lacking here in Voigt model is we don't have this elastic component, elastic deformation, but we have elastic deformation component in Maxwell. So if you combine these two, we can, sorry, not these two. Here we don't have any elastic deformation and recovery, but we need in actual polymer. So here we can combine these two, okay, we can get very accurate estimation of creep. I mean, it's an explanation of creep behavior of polymer. So what they have done is they have developed 4-parameter model. Like you take Maxwell as well as what? Voigt. One series and one series and this one series and one parallel together. So you have to write simply your total strain is what? Strain in component 1, Voigt element, and plus strain in Maxwell element plus strain in Voigt element. So both equation you already know. Just put your final expression will come. For 4-parameter model. So for 4-parameter model, it will come sigma naught by E1 and plus sigma naught by T into eta 2 plus sigma naught by E3 and what? 1 minus E to the power minus E to the minus T by tau, right? Tau 3. If you see, this is from Maxwell element, this one, and this is from Voigt element, this one. This one, okay, J sigma by E, okay. But again, I mean, this will give you very accurate 4-parameter model. But in 4-parameter model, we need E1, E2, you know, 2 type of modulus into a component, E1 and E3 and eta 2. Got the point? But we have only single E here. So it's better to use Voigt element, which is very good approximation of creep. Okay. So for it, an answer will be 1. Okay. Okay. Now, this question is very easy if you simply know what is the concept of percentage crystallinity and the heat of fusion. So your percentage crystallinity is heat of fusion of sample by heat of fusion for 100% crystalline sample. Okay, very simple. If you see, you have a PVDF, you quench it from melt in one case, in another case you slowly cooled it. So slowly cooled, it's telling you the percentage crystallinity of slowly cooled is 60%, and the heat of fusion for quench is delta Hm. Delta Hm is heat of fusion for slowly cooled. So M subscript, let's use M subscript for slowly cooled. So slowly cooled PVDF. Okay, means delta Hm it's heat of fusion or crystallinity is, I mean the enthalpy of sample is delta Hm and crystallinity is 60%. Right? So from here you can calculate the, and now if you see here, the heat of fusion for 100% is also given. So your delta H for 100% crystalline PVDF is also given 100 joule per gram. Now it's telling the heat of fusion for quenched. So let's say for quenched PVDF, I'm using subscript, let's say 2. So my enthalpy of fusion is, let's say, delta H2. Okay, and they're telling calculate the percentage crystallinity for that quenched one. So what is X2? So what is X2? X2 is enthalpy of that quenched PVDF divided by enthalpy of 100% crystalline PVDF into 100. And delta H2, what is delta H2? What is delta H2? So enthalpy of quenched one. It's telling enthalpy of fusion for quenched one is 0.5 times delta Hm. So delta H2 is 0.5 times delta Hm. Okay, so I can use 0.5 times delta Hm by delta H100 is already given 100 into 100. It's going to cancel out, of course. So you're going to get percentage enthalpy is 0.5 delta Hm. What is delta Hm? So from this data you can calculate, because percentage crystallinity is given 60%. So use this formula. Your 60% is enthalpy of sample. What is that? Delta Hm. So delta Hm by 100% enthalpy. What is that? This 100. This one. So 100 into 100. As you can see, delta Hm, that is enthalpy of fusion for slowly cooled, okay, is my 60. So I can use here 0.5 into 60. That will give you 30. So your answer is 30. It's very easy. Actually, you see, just see what is asking. Percent crystalline for quenched. So percent crystalline for quenched is delta enthalpy for quenched by enthalpy of 100% into 100. Simple. So delta enthalpy of quenched by 100% is 100 into 100. So delta H enthalpy of quench, if you know, you can calculate crystallinity. How to calculate this enthalpy for quenched? It's telling for quenched it is 0.5 Hm. That is 0.5 Hm. What is this Hm? This Hm is heat of fusion for slowly cooled. So it's a, if you have a slowly cooled, then enthalpy of slowly cooled is delta Hm. If it is given its crystallinity is 60% slowly cooled, so you can calculate, right? The crystallinity is enthalpy of its fusion divided by enthalpy of 100% into 100, and 100% is already given 100 joule, and this is 60. So delta Hm by 100 into 100, it's going to cancel out, right? So you got your delta Hm is 60, 0.5 into 60. You can get 30. It's not a very tough task if you know the simple calculation. Okay, answer is 30. Next one is very easy. I think it's a unit based. So density is given 0.9 gram per centimeter cube. volume is given 10 centimeter cube. What is being asked? And time is given 100 seconds. What is being asked? Output of the extruder in what unit? Kg per hour. By seeing your mass and time, its equivalent is gram per second. You want your answer in gram per hour. You can convert into kg per hour, but your answer you want in gram per second, right? How can you get gram per second? You have a gram per centimeter cube. You want to remove centimeter cube, so you can multiply centimeter cube here, and you want second in denominator, so you can add second here. If you notice, this is your density, and this is your volume, and this is your time. Knowing unknowingly, you know the formula from the unit. Of course, that answer will come in a gram per second. So your Q will be rho, that is 0.9 gram per centimeter cube into volume 10 centimeter cube divided by time. What is time? 100 seconds. See here, your centimeter cube is going to cancel out. Okay, so 0.9 into 10. Okay, it's a 9 by 100 gram per second. It is asking kg per hour, so you can convert that. It's not a big task. Okay, so 9 by 100, that is 0.009. 1 minute, गलती हो गया. 0.09, 0.09. Okay. Gram, 1 gram, 10 power minus 3 kg. And 1 second. 1 second kitna? 3600, right? 1 second is, 1 hour is, we have to convert second into hour, na? 3600 second. 60 minute, 60 into 60 second. That means 3600 second. So 1 second is 1 by 3600 hour. So I can write, instead of second, I can write 1 by 3600 hour. I can get now my answer 0.09 into 10 power minus 3 into 3600 kg. You can calculate here. You can get your answer. So the easy question is also there, but few questions are really tricky. So answer is 0.32. You can easily calculate it. Okay? Now, this question was very tricky because anyone who have learned Mark-Houwink equations without using common sense or dimension, understanding the dimensions or units. So if you see the Mark-Houwink equation, what does it tell? It tells that intrinsic viscosity can be, you can use intrinsic viscosity to calculate molecular weight of polymer. You must know Mark-Houwink constant. Here, what does this unit tells? The unit of intrinsic viscosity is what? What is the units of intrinsic viscosity? Deciliter per gram. Right? So, I mean, it's not a big task because see, eta is specific is a special value of eta is specific by C. If you plot eta is specific by C with C, the intercept is the intrinsic viscosity, right? That means it's a special. Of course, you have to put limit C tends to 0 or eta is specific. Special value of eta is specific by C is intrinsic viscosity. And what is eta is specific by C? Eta is specific by C is eta specific. What is that? Eta relative minus 1 by C. And what is the unit of eta relative? Nothing. It's a time by time. It's a unitless. So numerator is unitless, and C is the concentration. Now here is the point. The concentration could be gram per deciliter. Gram per deciliter. Your unit of intrinsic viscosity, okay, is going to be deciliter per gram. Or C could be also given in terms of gram per centimeter cube. Both option is given in definition of IUPAC. Okay, the unit of intrinsic viscosity. If you search on Google, yeah, from IUPAC. Okay. In that case, your unit will be centimeter cube per gram. Into this unit. Now, if this unit is, it could be deciliter per gram or it could be centimeter cube per gram. Okay. Then what should be the unit of K and A? I mean, right hand side cannot give you centimeter cube per gram. Remember, these techniques are relative technique. So this relation is empirical relation. Here it's not giving. By using unit of K and A, how will you derive the unit of eta? That's why by default, the standard, it is defined that the intrinsic viscosity unit will be either in deciliter per gram or centimeter cube per gram. Both is okay. Now using this equation, if you see the option given in this question, 0.2 gram is dissolved in 100 ml. 100 ml matlab 1 deciliter. Okay. So that means your C will be, if you are calculating in deciliter, if you're calculating in gram per deciliter, then your C will be how much mass? 0.2 gram by how much volume? 1 deciliter. So that means it will be 0.2 gram per deciliter. Or your C could be gram per centimeter cube. So each ml is each centimeter cube. So in that case, you can, your C will be how much gram by how much centimeter cube. That is 100 centimeter cube. In that case, your C will be 2 into 10 power minus 3 gram per centimeter cube. Now both C is okay. Both C is okay to put. The question is which C you will put here in calculation of here. Your eta is specific by C. So in Mark-Houwink equation, if you see Mark-Houwink equation, just put here. So eta is specific by C equals to K is given 0.001 and M, okay, M to the power A is given 0.5. Now eta is specific by C, you can calculate what is that? Eta is specific by C, what is given here? C is given and relative viscosity is given. So eta R minus 1 by C equals to 0.01 M to the power 0.5. Now if you're using C equals to in gram per deciliter, this value, okay, your molecular weight will come 6.25 into 10 power 6. And if you see the here, your molecular weight will be in the order of 10 power 10. So anyway, this is not okay. You will never reach up to 10 power 10. So you cannot use this C value in gram per deciliter. You have only choice to use gram per centimeter cube. That is 2 into 10 power minus 3. Now if you're using C value as 2 into 10 power minus 3, and eta R is 1.5, 1.5 minus 1 by 2 into 10 power minus 3 equals to 0.001 M to the 0.5. Now you can definitely get M equals to 6.25 into 10 power 10. That means your M will be your answer will be 6.25. I hope I made sense to you. 6.25. This is very straightforward question. Okay. Your VF is given 0.4. So DM will be automatically 0.6. Modulus of elasticity of fiber is given. EF is given 69 GPa, and VF EM is given 3.4 GPa. It's asking modulus of elasticity of the composite longitude is E1. So E1 equals to EF VF plus EM VM. You can use it. So some questions are direct straightforward. So they have tried to balance difficult and most very difficult and intermediate question. But somehow they have given so many MSQs that it is so horrible. The answer will be 10.6. Okay. This is a very easy question that you all know because your Ni is given and your Mi is given. So you can use weight average molecular weight. MW is summation of Ni square by summation of Ni Mi. Okay. So you can easily basically put, okay, so it is N1 M1 square plus N2 M2 square by N1 M1 plus N2 M2. I think I have only, this is N1, this is N2, this is M1, this is M2. You can put, you will get your answer. You should be getting answer around 6, 8, 7. Okay, so that's all from polymer science. So thank you all, and please don't forget to join our Telegram channel, because we'll be giving updates about our scholarship tests. So you can join our regular batches and prepare well. Okay, we'll be giving the updates, and it will be. Thank you all.